Hi, and welcome to the fifth and final episode in our series of videos exploring the whole area of quantum computing and quantum programming. So in the first few videos, we worked up a logic puzzle, represented that in a way that is amenable to solution through a quantum computing approach. And then we submitted that problem to an actual quantum computer, one provided by a company called D-Wave. And then finally, in this episode, we are going to look at some of the computational complexity around what we've just explored. So if we kind of think back to, for those of you who've studied computer science or software engineering in college, you may have studied complexity theory. And this is essentially the area of computer science that's looking at, well, how long does it take to solve certain problems given the nature of the problem itself? So let's kind of dive into that a little bit, not too deep, but just to understand enough about why we think this is an interesting area from a computational point of view and why quantum computers can offer us potentially a huge advantage over traditional classical computers. So as we saw in our setup, we had a 5 by 5 by 5 tensor, so therefore 125 binary variables. So that means that our tensor can be in any one of 2 to the power of 125 separate states. One of those is going to represent a valid solution, and every other possible state is going to represent an invalid solution. So one kind of naive approach you might think, if you're just kind of coming at this problem at the start, would be that we would represent a candidate solution as being a number between 0 and 2 to the 125 minus 1, and essentially then try to solve the problem using brute force by iterating through every possible state and by then identifying if we found a state that constitutes a valid solution. We can see here in the diagram, this is a kind of a representation of that 125-bit number with combinations of zeros and ones. And so if we think about, writing the code to that, you might consider it would look something like this. We would have some function or some method here to check whether the potential candidate solution is indeed a valid, correct solution. Obviously, I've omitted the code here. And then we have essentially a while loop, which says that let's loop over all possible states of that number from 0 to 2 to the power of 125. And then if the solution is correct, then we'll print out the number, which will constitute the correct solution, and then we'll stop. And otherwise, we'll just increment and go around the loop again. This looks like a fairly straightforward solution, and you would wonder, well, why would you not solve this problem this way rather than all of the hoops that we jumped through the previous one? And the reason is that the number of possible states is enormous, that even in a very simple problem like this, such a naive approach simply won't work. If we actually try to run this, this video would never end. This would never come. We would never find a solution. Why is that? Well, let's look at how big 2 to the power of 125 is. So 2 to the power of 125 is 4 by 10 to the power of 37. Well, that's hard. It's still a huge number, but it's hard to get your head around. So let's go ahead and write that out long form, and it looks something like this. So it's 4 followed by 37 other digits. It's an absolutely enormous number. So let's try and kind of get some intuition as to how big this really is. So let's assume that we could evaluate one state for every clock cycle on a 3 gigahertz CPU, which is fairly standard for a high-end laptop or desktop today. So that's 3 billion states per second. And imagine we could do that since the start of time, which is essentially 4.8 billion years ago. So how many states would a high-end laptop be able to evaluate if it was running literally since the start of time? So let's go and work that out. So we have 3 gigahertz, that's that first number here, multiplied by 4.8 billion years, 4.8 by 10 to the 9, times 365 days, 24 hours, 60 minutes, and 60 seconds. And if we were processing at that speed, we would be able to look at 4.5 by 10 to the power of 26 different states. Now this number, by 4.5 by 10 to the 26, is 11 orders of magnitude smaller than the number of possible states. So that's 100 billion times smaller. So essentially what it would mean is we would need 100 billion of our laptops, each evaluating 3 billion states a second, all running since the start of time, to cover the entire search space here, to look at every possible solution and to make a decision, is it valid or not. clearly this is completely infeasible and completely impossible. But it gives you a sense that even in a very, very simple problem like this, that if we take naive approaches to trying to solve them, they just don't work. These are exponentially complex problems, and that exponential growth just gets out of hand very, very quickly. And so it's for that reason that we need to take other approaches. Now, there are classical solutions that will work and solve this problem very quickly as well. As I said at the start, we don't, strictly speaking, need a quantum approach. But as these problems get harder and harder, and as we get more computational complexity involved, this is where quantum computers are going to step in and help us to solve these problems in a way or with a level of accuracy that classical computers won't be able to do. And that is why we and many others in the industry are so excited about this potential. So that concludes our 5-part series on exploring quantum computing and quantum programming. I hope you found it interesting and informative, and I hope it gave you a brief intuition as to how this space works and why we're so excited and interested in it. There are plenty of materials available online, so please feel free to explore and to kind of deepen your own understanding of this absolutely fascinating area, which I believe is the one of the future states of computing, and certainly it's a very interesting time to be able to participate in that. So thanks again, and hopefully we'll see you at a future video.